So, channel waveguides are the main elements of integrated optical circuits, which can be used to connect different components, and also they can be used to make many devices. So, typical configuration of a channel waveguide is as follows. We have a substrate, I am drawing the top view and also the all these projections. So, we shall worry about how to fabricate these later on, but you have a, you can assume that this can be formed by diffusing some material into the waveguide region. The cross section will look like this. So, in this region the refractive index is higher than in the substrate. So, if you launch light into the input of this waveguide, you can expect the light to propagate in this waveguide and exit at the other end. So, there are many other important configurations depending on the technology that we use to fabricate these devices. For example, the most popular being the silicon technology, where you have SOI waveguides. This one for example can be called as a diffused or buried waveguide. In the silicon technology, you have a silicon substrate and an oxide, and on top of that you form a what can be called as a ridge waveguide made of silicon. So, this is a cross section. So, the light propagates in this region. So, all these are channel waveguides or 3 dimensional, they can be called as 3D waveguides, because the light is confined in both x as well as y directions. Maybe let us call this as y and this is x. We will reserve x for the depth direction and y for the width direction, and the propagation direction is z. So, now let us start with the scalar approach. We have been following scalar approach for the slab waveguides, symmetric slab waveguide and asymmetric slab waveguide, and we have seen that you can relate the scalar approach with the vector approach when we need to deal with the polarization and other issues. In another discussion we will talk about the vector approach, but for the time being let us start with the scalar wave equation and see what are the modes of the channel waveguide, how to find out the beta, and how we can use the theory studied earlier of the slab waveguides to design and analyze channel waveguides. So, this is a scalar equation, reduced scalar equation. So, we have reduced it by assuming the time and propagation direction variation factor as e power I omega t minus beta z. So, all the fields psi have been assumed to be a function of only x comma y, x comma y comma z comma t. So, here the transverse Laplacian is given by del square with respect to x square and del square with respect to y square, and the most important input parameter is the refractive index profile n . N is a function of x comma y, compared to the slab waveguide where we have the refractive index profile depending only on either x or y. We have refractive index profile dependent on both x as well as y here. So, let us look at a very generic channel waveguide which can represent almost all types of channel waveguide. Of course, we will assume the refractive index profile to be constant in each of these regions. So, let me draw a typical, a general channel waveguide configuration. So, it will look like this. So, the refractive index is N1 in this region, N2 in the substrate region, N3 in the cover region, N4 side and N5. And you can also consider the refractive index in these corner regions, but to an approximation we can ignore the fields in the corner regions. It will not make lot of difference except when we are coupling the waveguides. This is N4 and let us call the depth as D and width as B and the coordinate axis in the middle. And as described earlier, let us assume y to be the width direction and x to be the depth direction. So, our objective is to find the wave function psi of x comma y or the mode field profile you can call it, and the propagation constant beta. So, taking clue from the earlier discussion about symmetric slab waveguides and asymmetric slab waveguide, we can express the fields to be oscillatory in the guiding region and exponentially or exponentially decaying in the substrate and cladding regions. But then you have a complication that is a function of two variables. So, by in each of the regions, by considering the field to be a product of fields in the varying in the x direction and fields that varying in the y direction, we can express the mode fields in each of the regions separately and then use the boundary conditions to find out what are the expressions relating the mode fields, the propagation constant and so on and so forth. So, in the region 1, I will use some other color, you can express as psi 1 x comma y. I am assuming the field, the refractive index to be constant in each of these regions, even though it is different across the regions. It is a step index channel waveguide. So, when we separate the field in terms of x and y variations depending on the oscillatory nature or decaying nature of the field, we can choose an trigonometric function or an exponential function for each of these x and y variations. And also we have seen in the asymmetric channel waveguide that it is a combination of sine and cos for trigonometric functions and exponential decaying and exponential rising for the decaying portions. So, we can say that the field variations are as follows. Instead of considering a sine plus b cos notation, we can put the other arbitrary constant in terms of the phase like this. So, in the region 1, a1 sine of kx, I will define all these constants as we go along to x plus some arbitrary constant psi multiplied by one more oscillating field ky into y plus eta. So, we can express the field in the guiding region as a combination of is a product of sine and cos, where kx and ky are constants representing the variation of the field along x and y directions oscillatorily. Similarly, in the region 2 we can express the field psi 2. This is region 2 where we have oscillatory nature in the x direction and exponentially decaying nature in the y direction. So, for that we can express the field as follows: A2 is an arbitrary constant, we can say exponential, or just a minute, sine of kx into x plus I, same as that earlier, but in the x direction, no, in the x direction it is exponential. I will call the decay constant as gamma 2 x minus d by 2 minus or plus, whichever, because that arbitrary constant A2 will absorb other arbitrariness of the constants, and along the y variation I will call it as ky multiplied by y plus eta. So, I am using the decay constant gamma 2, I will call this positive y direction, and d by 2, d is the depth. Similarly, I will write for the other regions. R3 is the region 3 where we have psi 3 of x comma y given by A3 into exponential minus gamma 3 x minus d by 2 multiplied by cosine ky y plus eta. And in the region 4 we can consider psi 4 of x comma y as A4 multiplied by exponential of, so in the region 4 here it is oscillatory with respect to x and exponentially decaying with respect to y. Finally, region 5 is similar to region 4 and we can express R5 in terms of an oscillatory field sine or cos kx into x plus I and exponential of minus gamma 5 y minus b by 2. I would suggest you to focus on the nature of the field and please take care of the arbitrary constants involved like psi 3 and eta and whether we make a minus b or plus b will depend on the coordinate axis chosen and so on. So, now we need to define a bit about the constants involved. You know that A are amplitude constants representing amplitudes, then K are constants representing spatial variation of the fields, that is the constants K, because they are used to represent the oscillatory fields. You can say they are spatial frequencies, and gamma can be called as a decay constants. But once again look more carefully at these constants K, which are used for different regions. So, in general you can say that Ki are the constants of the form k0 square n I square minus beta square, where the Ki could be the oscillatory constants kx ky or gammas, which are the opposite beta square minus k0 square n square I for decay purposes. So, in particular the constants k, the oscillatory constant k is important in the region 1, and we would like to call it as k0 square n1 square minus beta square, where k0 is 2 pi by lambda, and which can be expressed in terms of kx and ky as kx square and ky square. In other words, beta can be written as beta square is k0 square n1 square minus kx square minus ky square. This has got a special significance that if we are able to solve for kx and ky separately, we can find out the propagation constant beta. And of course, once you get the beta, we can find out the effective refractive index of the waveguide as beta by k0. Now, let me quickly put down the definitions for the decay constants. Gamma 2 is n1 square minus n2 square into k0 square minus kx square, and gamma 3 decay constant in the region 3 k0 square n1 square minus n3 square minus kx square. This is also second and third regions. So, both contains kx. And gamma 4 and gamma 5 will contain n1 square minus n4 square minus ky square, and gamma 5 gamma 4 square gamma 4 square and gamma 5 square will contain k0 square n1 square minus n5 square minus ky square. We have kx for gamma 3 and gamma 2 and ky for. So, effectively we need to worry about solving for kx and ky, which in turn would give us beta. So, in order to find all these constants, we need to have the boundary conditions, that is the fields at the interfaces. We can say that the fields are continuous, as we did for the slab waveguides. We can force the fields to be continuous across the boundaries, and also the derivative of the fields to be continuous across the boundaries. Just recall that the derivatives of fields could be related to the magnetic fields if the fields are related to the electric fields. So, if psi represents the electric field variation, the derivatives of the field could represent magnetic field variation or any of these components of this field. Depending on the way that you formulate the scalar wave equation, you can choose appropriate form of the Ez and Hz and relate them to the wave functions psi and psi dash. So, finally, we can say that we will obtain, like in the case of a symmetric slab waveguide, recall that we have got the equations of the form alpha equals k tan k w by 2, symmetric slab waveguide. And in the case of asymmetric slab waveguide, also we have a combination of this, like k multiplied by w minus tan inverse alpha by k and alpha 2 by k and tan inverse alpha 3 by k. So, effectively it is in terms of a transcendental functions of tan. So, similarly we can apply the boundary conditions and obtain the characteristic equations or the dispersion equations to obtain the values of kx and ky. So, I will just write down and summarize later on. I am using only a scalar approximation, kx into xi minus d by 2 is related to gamma 2 by kx, and tan of ky into xi plus d by 2 is gamma 3 by kx, and tan ky eta minus b by 2 minus gamma 4 by ky, and tan ky into eta plus b by 2 equals gamma 5 by ky. So, please check the arbitrariness of the sign used maybe. So, finally, we can combine these to get tan ky b minus ky into gamma 4 plus gamma 5 divided by ky square minus gamma 4 gamma 5 equal to 0, and also tan kxd minus kx into gamma 3 plus gamma 2 divided by kx square minus gamma 2 gamma 3 equals 0 or m pi, depending on when you invert it. You can introduce the constants m and n as the mode numbers. So, like the way we did for the slab waveguide, we can define the V numbers of the channel waveguide and express it in terms of the width and depth parameters. V number of channel waveguide. So, can be defined in several ways, but the most common way of using the V number is in terms of the width. As earlier, as for the asymmetric slab waveguide, it is in terms of the width parameter. We called it as B in this discussion. It can be expressed as n1 square minus n2 square, and also the normalized propagation constant B in terms of the propagation constant beta, normalizing propagation constant eta, n2 square divided by n1 square minus n2 square. So, this is one of the most useful ways, even though it does not exactly match with the definition for the asymmetric slab waveguide. And finally, we can solve for kx and ky, and we can express beta in terms of kx and ky and plot the VB characteristics. This is the definition for beta. So, like in the case of other waveguide problems, you end up plotting the VB characteristics, V on the x axis and B on the y axis for the channel waveguide, and typically you can expect the design curves as follows. But we would like to make it a point that that there is a cutoff for each of these modes, including the fundamental mode, and that depends on the geometry and asymmetry and so on and so forth. And also we are also not very certain about the cutoffs, successive cutoffs and the distance between them. It depends on the geometry and so on. But we can be sure that the B according to the definition is between the 0 and 1, and this is a very generic curve and can be compared with other waveguide configurations, and we can draw some conclusions based on the structure and the nature of variation of the propagation constant. So, more details of these mathematical expressions of this channel waveguide can be found in the textbooks, and also a specific there are several papers. So, one of them I am just quoting here. This is by Westerveld et al. IEEE OSA Journal of Light Wave Technology in 2012, volume number 30, number 14 and July 2012. So, I would like to finally mention that there is a very popular technique on similar lines originally devised by Marcatelli. So, this is a variation of the Marcatelli method and the most popular Marcatelli's method. There are many improvements of Marcatelli's method now, and there are also Mathematica programs. You can look at by these authors. We have a openware Mathematica MATLAB program which can be used to solve and compute the properties of the channel waveguide. We shall look at one more popular method to analyze the properties of the channel waveguide called the effective index method. Effective index method is a simpler method to analyze and design channel waveguides. Here the analysis of the given channel waveguide is split into two successive slab waveguides as follows. I will take a typical example rather than the generic example, the cross section of a buried channel waveguide with width W and depth D, refractive index N1 in the core region, refractive index N2 in the substrate region, and the can be devised in two parts. In the first part, we consider the horizontal slab of depth D and refractive index N1 and refractive index N2 for the substrate and for the cladding. And we know how to solve this problem as an asymmetric slab waveguide. So, in the effective index method, you find out the properties of this asymmetric slab waveguide, find out the beta or beta by k0, which is called the effective refractive index of the waveguide, and use it to devise another so called vertical slab waveguide. It is only a symmetric slab waveguide rotated 90 degrees of width W and refractive index N2 in the cladding region and N effective in the guiding region. So, the N effective obtained in the previous section is substituted for N effective of the vertical slab. This can be called as a depth wise asymmetric slab waveguide, this is width wise slab waveguide. So, in the particular case of example that we have considered, this is a symmetric slab waveguide along the width direction and a symmetric slab waveguide in the depth direction, and we have known all the expressions to calculate the effective refractive index of the asymmetric slab waveguide as well as symmetric slab waveguide. The crux of the problem is to find the refractive index of the first region and substitute for the slab region, and the final refractive index that we obtain, let us call it is NF, is the final refractive index of the original channel waveguide. So, we can prove this by substituting the operations in the scalar wave equation 2D scalar wave equation and then reducing the mode field expression, the wave equation for the expression for the mode field in terms of only a one dimension. Suppose we call it as x and y, we can say that we have only a equation for the x. We are reducing a 3-dimensional problem into a 2-dimensional problem. 3D waveguide problem is converted to a 2D waveguide problem. In other words, we can say that this waveguide is equivalent to the given channel waveguide and is quite easy to handle compared to the 3D example. So, this has got many advantages and many applications. We can use it for many other devices. For example, when two waveguides are close together, it is much more complicated to analyze. Suppose you have a problem like this, two waveguides are close together, this is called a directional coupler problem. We can reduce this into a 2-dimensional problem by using the effective index method, by finding out the effective refractive index of the first slab asymmetric slab waveguide and using that refractive index, the effective refractive index of the first region, and substituting for the refractive index of the guiding regions of the individual channel waveguides N2, NE and N2. So, a 3D waveguide problem is reduced to a 2D waveguide problem. There are several ways to solve this multi-layer slab waveguide problem. So, we would summarize all these things in the next few slides. Thank you very much.